Hello everyone. So we're going to be graphing some trig functions today, sine and cosine, and we're going to take a look at some transformations that will begin to happen to some of these. So the first one that I'd like us to look at is y equals 2 times sine of x. Alright, so what we're going to compare this to is like our parent function, y equals sine of x, which we should be fairly comfortable with now. 0, 0, 91, 180, 0, 270, negative 1, 360, 0, and that would repeat as we go through. What you're going to notice with 2 times sine of x is that essentially all of those y values will just double. So 0 times 2 is still 0, but 90 times 2 is going to be, or well, sine of 90 is 1. 1 times 2 is 2. Sine of 180 is 0. 0 times 2 is still 0. Sine of 270 is negative 1. Negative 1 times 2 is negative 2. And 360 will still be 0. So if I compare this to my parent function, again, you're just noticing that the y values have doubled. So as I go to graph this, I'm going to label negative 1, negative 2, oh, sorry, geez, positive 1, positive 2, negative 1, negative 2, and I'll go ahead and graph my function. And so if I were to compare this to the parent function, you'll notice that essentially it's just gotten a little bit stretched, if you will. And in fact, that is the word, or the key term, or type of transformation that we've done. So let's take a look at another one here. Let's take a look at negative cosine of x. So this is going to be related to our parent function for cosine. And if we bring that up for reference, something that we should be very familiar with by now, 0, 1, 90, 0, 180, negative 1, 270, 0, and 361. What's going to happen here is that this negative is essentially going to flip or reflect the graph. So I'm going to take all of these values and just make them all negative. So this will be negative 1, negative 0 is still 0, positive 1, 0, and negative 1. And now as I graph all of these, let's go 1, negative 1. So starting off down here, 90 still 0, 180 positive 1, 70 0, 360 negative 1. And we compare these graphs, you will see that from the parent function to this, it was just a reflection over the x-axis. So let's take a look at another graph right here. Let's take a look at sine of x minus 2. So this time, the new little wrinkle to this is that I have a subtraction at the end. So if I think back to my parent function for sine and all of these values, all I need to do to complete my table is take those values and subtract 2. So 0 minus 2 will be negative 2. 1 minus 2 is negative 1. 0 minus 2, negative 2. Negative 1 minus 2 down to negative 3. And 0 minus 2 down to negative 2. So as I go to plot these, I'm going to label this negative 1, negative 2, negative 3 for each of those coordinates. So at 0, I'm down at negative 2. 90, I'm at negative 1. 180 down to negative 2, 270 all the way down to negative 3, and 360 back up to negative 2. So all of my points on my graph now are negative. They're all below the x-axis. They've all been shifted down 2 units. As we think about the general properties of this graph right now, or this function, the period is still the same. Alright, so if I just talk about that for a second, the period would still be 360 degrees until I start to repeat myself. But what's happening here is that, the distance from top to bottom is the same also. All right, from my minimum point of -3 to my maximum of -1. I still have a range of only 2 units, but the actual, if we think about domain and range, domain would be all real numbers, and the range of this function, we would say that my y values are going from -3 to -1. And I would write that range as a compound inequality. So let's go ahead and formalize these little discoveries that we've been doing and talk about standard form for these two trig functions. So I'd pause the video at this point and go ahead and write all of this down. When I think about the generic standard form, any number out in front is going to symbolize a vertical stretch. And it's also going to be known as the amplitude. And so amplitude is a very important vocabulary word when we graph sine and cosine. And we're going to think of this as the distance from the middle. So it's easiest to understand when we look at the parent function of sine of x. If there's no number out in front, I would imagine that that is a 1, and the amplitude would be 1 unit because it is 1 from maximum to the middle, which would be the axis for the normal parent function. Same with down here. It's still a distance of 1 from the axis to my minimum point of -1. Hence the amplitude, distance from max or min to the center. And anything that is added or subtracted out at the end here is going to be a vertical shift. If it's a positive value, we're going up. If it's a negative, we're going down. And the last thing to formalize and talk about is that a negative a value causes a reflection over the x-axis. All right? So let's take a look at a couple of equations, and we'll name the amplitude and transformation from the parent function. So my amplitude is going to be 5. We could abbreviate this as AMP. And the transformation from the parent function, when I have an amplitude of 5, that means that I had a vertical stretch. So very informally, if we think of, my original sine graph being something like this, with an amplitude of 5, essentially you have the same starting point, but now I'm going up 5 times as much, and I'm going down 5 times as much. Right? And I didn't really make that symmetrical, just a rough concept of what would be happening here. All right? Let's take a look at example 2 here. It says name the amplitude and transformation from the parent function. Well, I've got no number out in front, so that means that my amplitude is just 1. But the transformation that's happening here is this -1 at the end. And that's going to symbolize a vertical shift. And specifically, that would be a vertical shift down 1 unit. Next example. So my amplitude in this function is going to be 3. But I have 2 transformations that are happening here. All right, this negative out in front is going to cause a reflection over the x-axis. And then this +4 at the end is going to cause a vertical shift. Specifically, up 4 units. In our next example, it wants us to graph as well as identify the transformation. Well, my transformation, if I have y equals 1/2 times sine of theta, is going to be this 1/2. And this is going to change my amplitude. So my amplitude for this is going to be 1/2. It's going to actually, since it got smaller, we're going to refer to this transformation as a vertical compression. So I wouldn't want to call it a stretch because it's not getting larger. It is in fact getting smaller. So what I can do here, since I don't have any of my y values labeled on the axis, is I can make them whatever I want. I could kind of make +1 up there and then 0.5, -0.5, and -1, so that when I think of all of my values that I'll be graphing, it'll be nice and easy for me. I'll have those half values. So for sine, if I think about, where I want to get some points here, if I have a x and y table of values, I'll use those 5 key x values 0, 90, 180, 270, and 360. And then my y values will just be half of what they'd normally be. So 0, 0 stays the same. But instead of 90, 1, it'll be 90, 1 half, which 1 half, 0.5, same thing. 180, 0, 270, negative 1 half, and 360 at 0. So I'll go ahead and graph all of these now on here. Oops. That is 0, 0, 90, 0.5. Disregard that. 180, 0, 270, negative 0.5, and 360, 0. And then I could connect these with a nice curve. And also ending with arrows pointing in both directions because it will continue. Next one here, I've got a negative 2 times cosine of x. And I want to graph this and also identify the transformations from the parent function. All right. So I've got two transformations. Amplitude is 2. I've got a reflection over the x-axis. And I also have a vertical stretch. Okay. So let's go ahead and make a table of values over here. Same x values. You are going to be writing these x values down a lot this chapter. Now, here's a little strategy that I'm going to do. I'm going to think about my parent function, or my coordinates from my parent function, cosine of x, and I'm just going to multiply them by negative 2. It really is as easy as that. I can kind of combine these two transformations and do them at the same time. So take that value of positive 1, which I'd start at, and this would become a negative 2 for my starting value. 0 times negative 2 is still 0. My value here would originally be negative 1 for the parent function, but times negative 2, that will send me up to positive 2. 0 times negative 2 is 0, and positive 1 times negative 2 is negative 2. So since I'm going from y values of negative 2 to 2, I'll just label my y-axis like so. I think that'll get the job done. And I'll start plotting my points. So 0, negative 2, 90, 0, 180, 2, 270, 0, and 360, negative 2. So as I go to plot these, something I'm going to do to help myself, key mistake that a lot of kids make is that they'll just start going from here to here. And that's how you get like these straight zigzag lines that don't look as curvy as they should. So since I know that this is the bottom of my valley, if you will, and that it's going to be like this, I can kind of draw that to help guide the shape. And same with up here, this is going to be the top. So I could put, that kind of shape right up there. And I could do the same thing down here. And then it just kind of helps guide the rest of your markings. Also ending with arrows on both sides. So there we go. We've got one more let's take a look at. So last one here is negative sine of x plus 3. So I do have that reflection over the x-axis. Sorry for the phone. And I do have a vertical shift up 3. So what I'd like you to do here, why don't you take a minute and pause the video. Go ahead and start with your x values that we've got here. And give this video a pause right now. Graph this on your own and then check and see how you do. Pause now. All right, take a look here. So with the reflection and the shift, your graph should be looking like this. That dotted line there was just drawn to help visualize where the center of the graph was. As we can see, I still have an amplitude of 1. Again, amplitude is distance from, max and min to the center. All right. If you had anything go wrong, make sure that you're doing these transformations in the right order. It's just order of operations. So multiply that original value by negative 1 and then add 3. All right. Thank you, everybody.